All right, so now what if we have force diagrams with friction, right? So let's say that we have this block that's sitting on a flat surface and there is an applied force directly in the positive x direction and we have static friction. Remember, static friction tells me that this object is not in motion. So what are the forces that I have? Well, I have my force due to gravity acting in the negative y direction, and I have that normal force pointing upwards in the positive y direction. Also, because I have static friction, it explicitly tells me I have static friction, I know that my static frictional force is going to have to be in the negative x direction. Why? Well, because if I didn't have a static frictional force, right, this object would be accelerating in the positive x direction. But because I have a static frictional force and friction opposes relative motion, my static frictional force is going to have to act in the negative x direction. So I can go ahead and create my force equations for this setup. So let's start in, I'm actually going to start in the y direction this time. So my summation of forces in the y direction is equal to mass times acceleration in the y direction. So what forces do I have in the y direction? Well, I have my normal force and I have this force of gravity and I have no acceleration in the y direction. Why? Because my applied force is acting completely in the x direction. There's no additional force acting in the y direction that would cause this thing to levitate up off of the surface. So it's going to be 0. So now I want to incorporate the directionality here. Remember that once I incorporate directionality, I remove my vector sign and I now have magnitudes. So my normal force is acting in the positive direction. My force of gravity is acting in the negative direction, and this is going to be equal to 0 still. So I can replace this force of gravity with the magnitude of my force of gravity. Remember that the vector for the force of gravity is equal to negative mg. So the magnitude of this vector is just going to be mg. So normal force minus mg is equal to 0. In this situation, my normal force is equal in magnitude but opposite in direction to the force of gravity, right? This is fairly straightforward because we have nothing acting in the y direction to change this. So what about the x direction? So I have a summation of forces in the x direction is equal to mass times acceleration in the x direction. Well, what forces are there? I have my applied force in the x direction, and I have my force of static friction in this x direction, and this is going to be equal to 0. Why do I know it's equal to 0? Well, I know it's equal to 0 because I have static friction. Static friction is telling me that it is stationary, it cannot be moving, so it's going to be equal to 0. The next thing I want to do is I want to incorporate my directionality here. So my applied force is in the positive x direction, and my force of static friction is opposing relative motion, so it is opposing that applied force. So this will be equal to 0. The next thing that I can do is I can recall that my force of static friction is going to be less than or equal to the coefficient of static friction times the normal force. So this less than or equals to, generally, in general physics 1 problems, they always say, like, find the moment at which the block begins to move. So if we want to find the moment at which the block begins to move, we can just assume that our force of static friction is going to be equal to the coefficient of static friction times the normal force. Why? Because of that plot where our force of static friction, right, increases up until we hit this equals, right? So this is less than, this is equals, and then it drops into that kinetic friction regime. So I can just assume that it is equals to, meaning that I can replace this Fs with negative mu sub s, right, coefficient of static friction, times my normal force is equal to 0. There's one more step here, right? I already solved for my normal force, and I know that my normal force is mg, so I can state that my force applied minus my coefficient of static friction times mg is equal to 0. And I know that in this situation, in order for this to be in static equilibrium, but on the verge of motion, my applied force has to be equal to that coefficient of static friction times the mass of the object times 9.81. So these are going to be my equations of motion for this specific setup. Now, what if I change this, right? And instead of having static friction, I have kinetic friction. If I have kinetic friction, I know that this object is moving. So I have my force of gravity still, I have that normal force still, and if this object is moving, it's going to be moving in that positive x direction, and my kinetic friction force will still oppose that relative motion, right? It's going to be slowing this object down. So I need to create my summation of forces. Well, to simplify this, right, my summation of forces in the y direction is going to be the same as it was in the last problem. We don't have any new force in this y direction. So I know from the last problem that my normal force is equal to mg. What's going to change is going to be this x direction. So my summation of forces in the x direction is going to be equal to mass times acceleration in the x direction. What forces do I have here? Well, I have this applied force, and I now have a force of kinetic friction. And because I have kinetic friction, I know this object is going to be in motion. It is going to have some sort of acceleration. I can now incorporate directionality. So I have my force applied minus my force of kinetic friction is equal to mass times acceleration in the x direction. And my force of kinetic friction is equal to mu sub k times my normal force. So I can replace this Fk with my force applied minus my coefficient of kinetic friction times the normal force is equal to mass times acceleration in the x direction. I know from the y direction that the normal force is mg, so the force applied minus the coefficient of kinetic friction, mass g is equal to max. And now my applied force with this kinetic friction and the motion is equal to mass times acceleration in the x direction plus my coefficient of kinetic friction, mass times g. I would generally simplify this, pull the m out, and have acceleration plus the coefficient of kinetic friction times g. So what is this telling us? This telling us that the force applied not only has to cause the acceleration, but it also has to be large enough to overcome that kinetic frictional force, right? So it has to have enough of a magnitude to produce the acceleration that we see in the system, as well as to overcome that kinetic friction. Right, so now I can do a block on an inclined plane, and I'm going to assume that this is moving, right? So I need to create my summation of forces in the x direction and in the y direction. So my summation of forces in the y direction is mass times acceleration in the y direction. I have a normal force, and I have this force of gravity in the y direction. And I know that this is going to have to be equal to 0 because my object with all of these forces is not going to end up levitating up off of the surface or sinking down into the surface, right? So the next thing I want to do is I want to incorporate directionality. So I have my normal force minus the magnitude of the force of gravity in the y direction is equal to 0. So I can actually replace this FGY with a different equation, right? So if we recall, our force of gravity is going to be the hypotenuse. Our angle, theta, is found here. So FGY is going to be cosine, because it's on the bottom. So if you don't remember why, go look at the non-friction video again. So I have my normal force minus Fg cosine theta is equal to 0. Fg is equal to mg. So my normal force minus mg cosine theta is equal to 0. This means that my normal force has to be equal to mg cosine of theta. So what about the x direction? Well, my summation of forces in the x direction has to be equal to mass times acceleration in the x direction. I have two forces in the x direction, right? I have this force of gravity in the x direction, and I have this kinetic friction force. I know that this kinetic friction force is pointing in the negative x direction because the relative motion of this object is going to be in the positive x direction. And I will have an acceleration. I'll know I have an acceleration because I have kinetic friction. So I can incorporate directionality. My FGX component is going in the positive x direction. My force of kinetic friction is going in the negative x direction. And I have mass times acceleration. I can replace FGX with the FG sine theta. It is sine because it is now opposite, right? And I can replace the force of kinetic friction with minus mu sub k times my normal force is equal to mass times acceleration in the x direction. I know that the magnitude of the force of gravity is just mg sine theta, and I have an equation for my normal force. So the normal force is going to be mg cosine theta is equal to mass times acceleration in the x direction. Now I can simplify this, right? I have mass in all three of my terms here. So this will simplify to g sine of theta minus mu sub k g cosine of theta is equal to that acceleration in the x direction. So one thing that you should think about is how would this change if I had static friction instead of kinetic friction?